Hi everyone, today we're going to look at horizontal resistor motion. Horizontal because we do not take gravity into consideration. When we start looking at motion in the vertical direction, then gravity comes into play and make things slightly more complicated, which we will look at a later stage. So basically friction. So when we say resistance here, we're generally speaking just a force that's going against the direction of motion. So whether it's friction, whether it's actual resistance in a fluid, or it's something that's being dampened. And here we treat them all of the same because they would just be a function of velocity, or sorry, a force proportional to velocity, or force proportional to the square of the velocity, which we'll look at separately later on. Big thing is in this topic, resistance can be examined with respect to both time and displacement, with a slight bias towards displacement here. A quick note on terminology. Resistance, when people talk about resistance, it usually very specifically refers to the force. So resistance is the force, and the retardation is the actual slowing down, the acceleration. So just a quick note on terminology. Okay, let's move on. So firstly, resistance that is proportional to velocity. It's usually experienced at low speed. So at low speed, the faster you go, there's a linear relationship between how fast you go and how much force that's pushing against you. So here, F equals to negative kV. So as you can see, K is the constant term. As V gets bigger, F will get bigger in the opposite direction, and that's a pretty straightforward relationship. And Newton's second law, we can always express force as mass times acceleration. So m times x double dot equals to negative k times v. So that's what we're going to work for the most part. Now, what we end up with this relationship is a differential equation where, in fact, I can write it as dv over dt equals negative k over m times v. Alright, so a differential equation where the derivative, the time derivative of v equals to v, like a multiple of v. So you can already tell now, basically, it has to be something exponential, because exponential functions are the only class of functions that really satisfy this property. But we're actually going to go through the process and give a very definite function for time function for v. Yeah, so obviously the quickest way is like we did a differential equation, dt over dv equals to negative m over kv. Yeah, and then we integrate both sides with respect to dv. Of course, they cancel out, and then what we end up with is dt equals to, because m and k, unless it's traveling really fast, mass and this proportionality constant will more or less stays the same. So we can just pull them out. Of course, here what we end up with is t, because we integrate 1 with respect to dt equals to negative m over k. So 1 over v, obviously, that leads to log of v. I'm not going to bother with I'm not really going to bother with absolute values because velocity here, we generally treat the direction of motion as positive. Okay, and then of course plus c. Okay, so now we just have to rearrange things to make it all into a to make it all into a function with v as the subject. So so log v equals to t times, so it's minus k over mt. Because it's a constant term, so I'm just gonna make it into c, because like negative c, positive c, like we should always treat it as a positive c. And then we raise both sides to the power of e. Yep. So we end up with v equals to e to the power of minus k over mt, and then e times c. So it's basically in the form of a e minus k over mt. As I mentioned earlier, it has to be a exponential function, and indeed it is. Now, what is a? So with all exponential functions, you know a must be the initial value. So when t equals to 0, so we have let's say the initial v is v0. Then we can just substitute in. So v0 equals to a, yeah, because this becomes 0, so that's it. And then v equals to or initial velocity times e minus k over m times t. Okay, so what does this show us? Now, if you think about it, it just means that it starts with initial velocity when t is 0. So as time passes, as t gets bigger and bigger, this number becomes more and more negative. So it's basically a case of exponential decay. What you end up with is, if here is your v0, or over time, the velocity will just... all right, that's horrible. Velocity will just like, look, this is the way the velocity will drop. Okay, now this is the resistance in terms of time. Let's look at resistance in terms of displacement. So it's a very similar procedure as we can see here. Here's one I prepared earlier. So because we're looking at displacement, so we treat acceleration as a v times v dv over dx. Everything else is more or less the same. So v dv over dx equals to negative k over m v. We divide both sides by v, so we have dv over dx equals to negative k over m. And then we can just integrate both sides with respect to dx. So we just end up with cancel out, so we end up with v equals to negative k over m x plus c. Okay. This is pretty straightforward. Now here, let's find what c is. Most cases, we usually start counting where x equals to x0. Rather, we start counting at when x0 equals to 0. So the initial displacement we treat as 0, and then as it moves, displacement changes, we end up with some value x. So here what we can do is v equals to negative k over mx plus c. So we know that when displacement is 0, so at initial place, v equals to whatever the initial velocity is. So v0 equals to basically c. And what does that lead us to? That leads us to v equals to the initial velocity, because that's what c is, minus k over mx. Okay, so this is interesting because this is a linear relationship. So if linear, basically you start off with a initial velocity, and then as distance goes on, the velocity decreases linearly as the distance increases. So it's basically some relationship like this. Okay. So for each unit of distance travels, the same amount of velocity is lost, giving us a linear decrease compared to the previous one, where when the velocity goes compared against time, it slows down exponentially, while compared to displacement rather, v decreases in a straight line. Yeah, that's pretty straightforward. Now let's look at what happens when resistance is proportional to the square of the velocity. Yeah, it's exactly more or less the same as previously. Mass times acceleration, so the force is negative proportion to the square of velocity. The bigger the v, the bigger this value, the whole thing becomes more negative, means more force. The whole thing becomes more negative, and the bigger force going against the direction of your velocity. So from a, once again, we can come up with the function of time, well, velocity as a function of time, rather. There should be a 2 here. Okay, so we're going to do more or less the same thing as previously. So dv over dt equals to negative k over mv squared. And then, of course, we have to turn things upside down so we can integrate it. dt over dv equals to negative m over kv squared. And of course, we have to integrate both sides with respect to dv. Okay, they cancel out. So we end up with t equals to negative m over k 1 over v squared dv. Okay, so this one we have to use the power rule, so t equals to negative m over k. So this is times negative 1 over v plus c. Yep. Okay. So we multiply both sides by, oh, it cancels out. So m over kt equals to 1 over v plus c. Of course, so which means 1 over v equals to mk over t plus c, because c is a constant. We can just absorb negatives into it very easily. And of course, we have to get a so v itself, get a function of v, so v equals to m over kt plus c. Okay, from here we need to work out what c is. So do you remember when t equals to 0, v equals to some initial velocity, so this becomes 0. So v0 equals to 1 over c, because m over times t becomes 0, and well, c is just 1 over v0. And if we put everything in, we have v equals to 1 over mkt plus 1 over v0. And if you really want, you can multiply everything by v0, so v equals to 1 over mk, all right, v0 t, so v0 minus 1. So if you want, if you don't like this, but it makes no difference in the end. Okay, so what you end up with is, as you can see here, it is it is a how should I say the right half. If v is positive, then it will become, sorry, if t is positive, this will be the right half of a parabola, wouldn't it? So the curve will look something like this. It will have actually a very similar shape to the previous one, to exponential curve, but with some difference in actual curvature. But still, as you can see, as time increases, the v gets slower and slower, but amount of decreases also decreases over time. So it will be a curve that's quite similar to the previous one, where it's just proportional to velocity, but there will be some differences. Okay, now let's look at how to examine it in terms of displacement. So here, we're going to do exactly the same thing as when we look at proportional to the just the velocity itself. So we end up with v dv dx equals to negative k over mv squared. So what I'm going to do is I'm just going to divide both sides by v squared. So, okay, I'm just going to simplify this into v dash over v, because otherwise it will be way too messy. Okay, so equals to negative k over m. Okay, so what we can do now, can you see that the v here, the v dash is derivative of the bottom, top is derivative of the bottom, and because, in fact, I'm going to emphasize this point, because v dash over v, because velocity here is going to be a function of x, so I'm just going to emphasize that it is in fact, they are in fact functions of x. So if we can, because they're both functions of x, we can just integrate them with respect to x and do the same on the other side as well. So obviously, derivative on top, function itself at the bottom, that's a log function, isn't it? So log v equals to, well, here is just a negative k over m times x, yeah, plus c. All right, so from here, we have to find a way to make v the subject. So we'll just raise both sides to the power of e. So we end up with e negative k over mx times e power of c. So v once again is it is a exponential function. Okay, so from here we can try to find a is by using the initial values. So let's assume it start off at 0. So when t equals to 0, oh, sorry, yeah, so when v equals to 0, rather. Oh, when x equals to 0, so where it's initial before it have moved anywhere, v equals to some initial velocity. So what we end up with is v0 equals to a, and conveniently enough, we can say v equals to some initial velocity, e minus k over m times x. So this is the sorry, this is the velocity in terms of displacement. So if we want to graph it, once again, it's you won't know what this looks like. So you have the v here, and then it decreases as the displacement goes on. Okay, so this is one way of approaching it. There's also a slightly different way of doing it. So the second way is is to treat it like what we did in when we dealt this velocity in terms of time. So we treat it as a differential equation. So we divide both sides by v this time, so it's dv over dx equals to negative k over mv. And then, of course, we can turn everything upside down because so we can integrate with respect to v. So it's dx over dv equals to negative m over kv, and we integrate everything with respect to dv. So what we end up with is, of course, this is just x equals to what is this? Negative m over k. 1 over v is just log v. Yep. Log v plus c. Okay. So once again, we can just simply rearrange everything. So log v equals to negative k over mx. Well, we're just gonna plus c, and of course v equals to v equals to e to the power of negative e to the power of c. Oh, you know how it goes, yeah? Oh, sorry, x. You know how it goes. It's exactly the same as one. It's just v equals to v 0 initial velocity times e. So either way it works, it makes no difference in the end. Yeah. So do whatever you want, really. Now let's have a look at a few examples. So firstly, the scenario is pretty straightforward. You have a boat that comes to a finish line and then slows down until it comes to a stop. The force of slowing down is slightly more interesting because it's a combination of a force that is proportional to square velocity and a force that's proportional to velocity. Okay. So what we can write it as is, our mass is already 1,000 kilograms, so 1,000 x dot dot has to equal to its opposite direction, so it's negative of 100 v squared plus 10 v. Of course, we divide everything by 1,000, so x dot dot equals to negative v squared over 10 plus v over 100. And then what we have is, because we're dealing with v as a function of x, so we have to turn this into something to do with v and x, isn't it? So it's v dv over dx equals to, we might as well combine all of this, so it's negative 10v squared plus v over 100. And then we divide both sides by v, and we end up with dv over dx equals to negative 10v plus 1 over 100. Okay, so this part is straightforward, and then we can just do exactly the same what we did previously. So we to be able to integrate both sides, we turn everything upside down. So we have dx. Actually, I will start a new line. So dx over dv equals to negative 100 over 10v plus 1. Of course, we can now integrate both sides with respect to v. And we end up with, of course, here, because dv cancels out, so we only have x equals to, what does that give us? So what we need to do is pull 10 out. And then what we have is 10v plus 1. So that what's on the so you have a derivative of the bottom on top, which means x equals to negative 10 log 10v plus 1 plus c. Okay, so to find what c is, we know that when x equals to 0, so at the finish line, c equals to 5 point, correction, v, so when x equals to 0, v equals to 5.5. Okay, so 0 equals to negative 10 log 55 plus 1, 56 plus c. So obviously, c has to equal to 10 log 56. And then substitute everything in. X equals to negative 10 log 10v plus 1 plus 10 log 56. Okay, so by rearranging everything, so here, I'm just going to do is just divide both sides by negative 10, actually. I'm just going to divide by both sides by 10, so we end up with x over 10 equals to log, because we have log 56 minus log 10v plus 1, so log 56 over 10v plus 1. And then we raise both sides to power of e, so e to power of x over 10 equals to 56 over 10v plus 1. And of course, 10v plus 1 equals to, so 56 divided by e to the power of x over 10. So it's 56 e to the power of negative x over 10. So in the end, if we rearrange everything, we have v equals to 56 e negative x over 10 over, sorry, minus 1 over 10. So that's our function. Now, how far correct to the nearest meter does the boat eventually travel as it comes to a stop? Well, really, we can just use the relationship here, can't we? Because what we're after is when v comes to a 0. So so we can basically use this relationship. So as v approaches 0, x over 10 will become approximately log, basically this, as v becomes 0, this part, this the lower part disappears as v approaches 0, so we end up with log 56, and x will equals is approximately 10 log 56, which is approximately 40 meters. And that's pretty much it. Okay, now let's have a look at the next example. So here, 5 kilo object is resist. So we can write it as 5 x dot dot equals to 1 over 10, or rather negative 1 over 10v, because it's in the opposite direction. So yeah, we can divide everything by 5, and because we're operating where it's where it's in relation to the displacement, so we have to write as we can do v dv over dx equals to negative 1 over 50v squared, and we can divide both sides by v squared. We end up with v dash over v equals to 1 over, sorry, the negative 1 over 50, and then we can integrate both sides with respect to x. So what we end up with here is log v equals to negative x over 50 plus c. Okay, so from here we can say that v equals to v would equal to e to the power of negative x over 50, and then e to the power of c. Okay, so what we need to find is what e to the power of c is. So as before, when x equals to 0, v would equal to some initial value. So so c has to equal to v0. So v equals to v0 e to the power negative x over 50. Okay, so this is pretty straightforward. Now the second part, when it has to slow to a quarter of its initial speed. So a quarter of initial speed means it's a v over 4, isn't it? Equals to v. So we have to find the x value for this equation to work out. Okay, so now what we end up with is so divide both sides by v0, so end up with e negative x over 50 has to equal to a quarter. So x ends up has to be negative 50 times log 1 over 4, which means x is approximately 69 meters. This is actually a very interesting result, because it means as you can see here, the initial velocity is irrelevant as long as the mass is 5 kilograms and the resistance is like 1/10, or rather proportional to the square of velocity, then the stopping distance will always be the same. And so regardless what the initial speed is, for the speed to reduce by a quarter. Okay, let's now look at another one. Right, so now we're trying to link displacement formulation with time formulation. So from this expression of velocity in terms of displacement, we now trying to turn it into displacement as a function of time. Oh, that's something we can do earlier because we did look at the how to formulate velocity as a function of time, and now we're gonna try to link this one. So what we have here, obviously, v equals to, so in relation to time, with respect to time, then v equals to dx over dt, isn't it? So dx over dt equals to v0 e negative k over mx. So that's what we've established earlier. And then from there, we will convert it all into something with respect to time. So what we need to do is, obviously, we need to be able to integrate this with respect to something. So here, the best option really is to integrate with respect to time. So we end up with dx equals to, so 1 over v, but 1 over this. So this, it becomes e k to the m, because 1 over this becomes positive, and then 1 over v, so v gets sent to the bottom. So, and then what we can do is we can integrate both sides with dx. Okay, what do we end up with? Dt over dx, so dx, they cancel out, so we end up with t equals to this one, which means we have to divide what's on the front. So and what do you get? So we end up with m over k e k over mx over v0 plus c. Okay, so what we need to do is now we'll have to rearrange all of this stuff to turn it into a function of t. So x equals to a function of t. But here we need to find out what c is first. So when t equals to 0, so when x equals to 0, so we can just assume that t equals to 0, x equals to 0. So 0 equals to m over, because when x equals to 0, this part disappears. So k v0 plus c, so c just equals to negative m kv0, and then plug it back in. T equals to m over k. I just combine everything together really. E k over m x v equal to 0 plus, oh sorry, rather minus m over k v0. Okay, so now all we need to do is all the algebra to get everything into the form where x is the subject. So m e k over m x over kv equals to t minus m over kv0. So multiply both sides by kv0. M e k over mx equals to kv0t minus m, and then divide everything by m. E k m x equals to kv0t over m sorry, it should be plus, so plus 1. Yeah, so now continue on from that. So k over mx equals to log of everything there, kv0t over m plus 1, and of course x equals to m over k, kv0t plus 1 over m. Okay, so here's our answer. Okay, so with this information, this is what we can get from the displacement. And if you really want, you can go back to this original slide, trying to integrate this with respect to time and see if you can get the same thing. Well, obviously you probably should, because as you can see here, this part v0 is close enough to the derivative of what's on the bottom to end up, when you integrate it, to end up with some kind of a logarithmic function. Yep. And now let's look at the last example. Yeah, so this one, we're actually looking for a specific time value. So what we can do is exactly the same what we've done so far. So we can just treat it as basically x dot dot equals to negative k over mv squared. And then because this time we're dealing with this time, so we have to say dv over dt equals to negative k over mv squared. And of course, to be able to integrate it, we have to turn everything upside down. So negative m over kv squared. So we integrate this with dv. We integrate this with the dv as well. So we end up with t equals to, so actually, we can just say m over k 1 over v squared dv. So the thing is, because we are actually integrating a function of v from one bound to the other. So you can see that this is the lower bound and this is the upper bound. So we can treat it like a definite integral. So we can write as t equals to negative m over k integral from v0 to v0 over 2 1 over v squared dv. Okay, yeah, and of course we can integrate this quite easily. So t equals to negative m over k. So it becomes 1 over, so it becomes negative 1 over v. So v0 or v0 over 2, and of course this one, the negatives cancel out, so you end up with t equals to m over k equals to so 1 over v0 over 2, so it's 2 over v0 minus 1 over v0, so equals t equals to m over k v0. And that's our answer. Then that's how some basics of dealing with resist motion. And so there is that.